Hello, I would like to welcome you to lecture 26 of ENG3N03. We'll discuss in this lecture a number of bias networks used for biasing transistors. We'll discuss a graphical explanation or graphical illustration of the BJT using BJT as an amplifier, and then I will show you a number of examples. Later in the course, we'll discuss how to use small signal analysis to be able to determine exactly the gain of a bipolar junction transistor. There are a number of networks or resistor networks and so on that we can use to bias a transistor. One of them is a voltage divider, and this one uses two resistances, R1 and R2, and they simply give the base a certain voltage relative to the emitter. And even though it's used it's called a voltage divider, it's not exactly a voltage divider as in the case for most transistors or for JFETs, because there is some tiny current flowing into the base. So we cannot ignore this current. And the easiest way of handling something like this is simply to replace all the network to the left of the base by its Thevenin equivalent. So we replace this whole network which connects the base. We replace it by a Thevenin equivalent. So now we separated the source. This is a source connected to the collector side. This is a source connected to the base side. These two are equivalent. It's the same voltage. Now we're going to replace all this side by Thevenin equivalent. So V Thevenin is equal to VCC multiplied by R2 over R2 plus R1. R Thevenin, you simply short out this one, you get R1 in parallel with R2. And then you can proceed with your analysis to find the base current, and then from that we can get the rest of the currents. So as I explained, we replaced everything connected to the base by a Thevenin equivalent. So we have now R Thevenin and V Thevenin. We can simply say now that the base current flowing into the base can be obtained by an expression. So if you consider this loop here, we can simply find the base current. So we can simply say that V Thevenin is equal to I base multiplied by R Thevenin plus VBE plus I emitter multiplied by multiplying R emitter. I emitter and I base are not independent of one another if we assume forward active region, because I emitter is equal to I collector plus I base, and I collector in the forward active region is equal to beta DC multiplied by I base. So really, writing the Kirchhoff voltage law in this loop has only one unknown, which is I base. Or this is the only unknown in this loop. So this is the bar that we have. So V Thevenin is equal to I emitter R emitter plus VBE plus I base R Thevenin. Sometimes they can simplify things because I collector is approximately equal to I emitter, as we agreed earlier, because I base is too small. So sometimes they replace I emitter by I collector, as was done here. And then we replace I base by I collector over beta DC. You can, of course, don't have to do that. You can as well replace I emitter by beta DC plus 1 multiplied by I base. It will give you a very similar answer. But this approximates it a little bit or simplifies a little bit. So now we can subtract V Thevenin minus VBE and then divide by everything else multiplying I collector. So for this one we are able to solve directly for I collector, and then once you know I collector, the current flowing into the collector, so this one here, once you know I collector, you can determine the voltage VCE, and VCE is simply equal to VCC minus I collector R collector minus I emitter R emitter. But as I mentioned earlier, I emitter can, for simplification, can be taken to be equal to I collector, or you can simply replace it as I emitter equal to I collector plus I base if you want to be very precise. This will create very little error in our calculations. And this is what's happening here. In this expression, to get VCE, the voltage between the collector and the emitter, we assumed that the I collector is equal to I emitter, and this is what you have here. Okay, let's take a look at an example. We have this circuit here. Beta DC for this transistor is 100, and VCE said is equal to 0.2 volts. Would like to find the operating point. VCE and IC is really our operating point. And would like as well to check whether this transistor is saturation or not. So as you can see, this biasing here gives the base certain voltage related to the emitter. So it's trying to turn on the base emitter junction, base emitter diode here. So we can assume we are in the forward active region, and then to proceed to do the calculations. I will replace all the components connected to the base by its Thevenin equivalent, and then we try to simplify from that point. So as I said, we find first the V Thevenin, and V Thevenin is VCC by R2 over R1 plus R2. R2 is 5.6 kilo ohm, and R1 is 10 kilo ohm. Then it's approximately 1/3, a little bit more than 1/3. So we get that V Thevenin is equal to 3.59 volts. R Thevenin, as I explained in the theory, is R1 in parallel with R2. One of them is 10, and the other one is 5.6 kilo ohm. You multiply them, you divide by 15.6, you get surprisingly also 3.59 kilo ohm. So V Thevenin 3.59 volts, and the R Thevenin 3.59 kilo ohm. Now we write a Kirchhoff voltage law around this loop. We assume the transistor in the forward active region. So VBE is equal to 0.7. So we can simply say that V Thevenin is equal to IB multiplied by R Thevenin plus VBE plus I emitter multiplied by 1K. And then we can replace I emitter by beta DC plus 1 I base. Beta DC I base is the I collector plus I base, because I emitter is equal to I collector plus I base. So this is one equation, only one equation that's function of one unknown, which is IB. So now we subtract V Thevenin minus 0.7, and then we divide by R Thevenin plus beta DC plus 1 multiplied by 1K to solve for the base current. So when you do that, V Thevenin 3.59, VBE is 0.7, R Thevenin we calculated 3.59 kilo ohm, beta is given as 100, R is 1 kilo ohm. If you put all this together, and here I did not really put this in kilo ohm, I left it as it is, but I know that the result will be in milliampere. So if you subtract these two and then you divide them, this is a big number, 101K. So the sum here will give you 104.59. So I base will be very small, 27.8 microampere. If you want to find the collector current, you simply multiply I base by beta DC, and you end up beta is equal to 100. So this will give you 2.78 milliampere. We have, of course, to check that our assumption forward active region is okay. So we have to find from the external loop, we have to find the voltage VCE. So if you remember, this is the loop looked something like this. You have your voltage, you have R collector, you have the transistor, and then you have RE here. So I want to evaluate VCE, because if it's below the saturation threshold, then the transistor is saturated. So here we can simply say that VCC is equal to I collector R collector plus VCE plus I emitter R emitter, or that VCE is equal to this expression. VCC is known, I collector already calculated that, I emitter is simply equal to I collector plus I base. You can see it's very close to I collector. This is why sometimes they simply ignore this difference, and then they replace I emitter by I collector directly. Now if you do all these calculations, this VCC is 10 volts, I collector 2.78 milliampere, RC, the resistance here, is 1 kilo ohm, R emitter is also 1 kilo ohm, and to find I emitter by adding 2.78 milliampere, which is I collector, to the base current, which is 27.8 microampere. Now if you do all this, you end up by VCE 4.42 volts. It's way greater than saturation threshold, and in that case we know that our transistor is indeed in the forward active region. Another possible topology for biasing a bipolar junction transistor is called base bias, and here you can see what they do. They connect the base directly to the supply voltage through a resistance RB. What's going to be happening, there will be a current flowing into the base, and this current will bias the base emitter junction and create the 0.7 volt needed here. And this circuit is usually used as a switch. So you can use as a switch by applying certain voltage to the gate and so on. You can modify it a little bit, and you can use it for an on-off switch with a BJT. The calculation for this one is extremely simple. We can assume here that there is a base current flowing in, I base flow in, okay, and this is a collector current IC, and of course this is IC here, and this is the emitter current I emitter, okay. So we can simply find IB by writing Kirchhoff voltage law for this loop. This is a loop here, okay. So we can simply say that VCC is equal to IBRB plus 0.7. Extremely simple. In this one you can solve directly for IB. Once you know IB, you can find the collector current and so on. This is very similar to what I said. The only difference is that they replace IB by I collector or beta DC and then solve for I collector. It's exactly equivalent. There is no difference. Once you have found IB and IC, you go back and then you have to verify that you are indeed in the forward active region. Then you have to find VCE. VCE in this case is simply equal to VCC minus IIC multiplied by RC. So this is this one here, and this has to be greater than the saturation threshold to be indeed in the forward active region. Okay, let's take a look at this example here. This is very similar. This is a base bias approach. We have this 100 kilo ohm. This is 560 ohm, and beta for this transistor is 85. VCE sat is 0.2 volts. So we'd like to determine what is the operating point, I collector and VCE. We'll apply exactly the steps I explained earlier. You write Kirchhoff voltage law for this loop. This will enable you to solve for I base, and then because you assume that we are in the forward active region, then the collector current will be equal to beta I base. Then we found I collector, and once you have I collector, you can check VCE. You can find VCE is simply equal to 12 minus IC multiplied by 560 ohm, and then you can verify whether you are indeed in the forward active region or in the saturation region. Okay, so these are the steps. This is 12, this is 0.7 because we assumed forward active. This is 12 minus 0.7 over 100K. You get that I base 117 microampere. Now we can find the collector current flowing here in the collector to the collector. It's BDC IB. Beta DC is simply 85. IB 117 10 to the minus 7. 10 minus 6, this will give you 9.61 milliampere. So now we know the collector current. Our last step is to find VCE, the voltage between the collector and the emitter. So this is VCE here, okay, plus and minus VCE, and we find it simply through this loop. This is the external loop. 12 volts is equal to 560 multiplied by I collector plus VCE. This is what you do here. 12 minus 560 multiplied by I collector that we calculated earlier, you get 6.62 volts. So the voltage between here and here is 6.62 volts, which is way hard saturation voltage. Then we are okay. We are not in the forward. We are in the forward active region and not in the saturation region. Another type of bias network is called the emitter feedback. It's similar to the base feedback, except that there is additional resistance here connected to the emitter. And again, the operating point for this one can be found very easily. You can of course use this loop here, external loop, assume 0.7 forward active region. You get VCC is equal to IBRB plus VBE plus I emitter R emitter. And then what we do, we can replace I emitter by beta plus 1 I base. Because this is really the general thing here. I emitter is equal to beta DC plus 1 multiplied by I base. And in many applications, they simply ignore this one, and they write I emitter is beta DC I base, which is equal to I collector, and this is what we have here. This will create very little error in our calculations. So in this implementation, as you could see, what they did, this is exactly the equation I wrote earlier, the equation for this loop, but I base was replaced by I collector over beta DC, and I emitter was replaced by I collector. So the only unknown here is simply I collector. You solve for I collector, and once you have I collector, you can find VCE, because VCE is equal to VCC minus I collector minus I emitter R emitter. You can of course take I emitter to be equal to I collector, or to be more precise, more accurate, you can assume that you can write I emitter equal to I collector plus I base. Okay, one other biasing network which we can use to bias transistors is called the collector feedback. And for this one, there is the base is connected to the collector, not to the VCC, not to the supply voltage, through a resistance RB. Again, the procedure is pretty the same. This is I base, this is I collector, and what's flowing out here is I emitter. So this one is here is I emitter, and this one here is also I emitter. Because of the topology, the current flowing here is equal to I collector plus I base, but I collector plus I base is I emitter. So this current is equal to this current. We can write Kirchhoff voltage law in this external loop. If you assume forward active region, VB is equal to 0.7. So we can simply say that VCC is equal to I emitter multiplied by R collector plus R base multiplied by I base multiplied by R base plus 0.7. Of course, I can get rid of I emitter and then replace it by beta F plus 1 or beta DC plus 1 multiplied by I base. So I have only one equation in terms of I base. And then you can get the collector current, or we can do it in the way that's explained here in the theory. Exactly the same thing. What they do, they simply ignore I base relative to I collector. This is the I emitter. This is I emitter here, which is multiplying R collector. They ignore this one here, and then they replace I base by I collector or beta DC. So they write it as one equation in terms of IC, and once you have IC, you can simply solve for the voltage VCE, because VCE is equal to VCC minus I emitter R collector, or we can simply write it this I emitter as I base plus I collector, or they can, as they do here, they simply replace I emitter by I collector. They simply ignore the base current because it introduces very little error in our calculations. Okay, let's take a look at one more example here. We have this transistor circuit. This is 10 volts here, this 10K. This one has beta equal to 100 and this 100K. Follow exactly the same procedure I explained earlier. There's a current flowing here. This current is equal to I collector plus I base. This is I collector here, and this is I base here. Okay, so what we can say is that 10 volts is equal to this current, which is I collector plus I base multiplied by 10K plus I base multiplied by 100K plus 0.7. There's a 0.7 between here and here. And we can replace, of course, this current, which is this current flowing into this one here. This current flowing here, we can replace it by I base plus I collector, and I collector is simply equal to beta DC multiplied by I base. So as I explained in the previous slide, we write Kirchhoff voltage law for this one. 10 volts equal to I emitter by 10K plus I base multiplied by RB plus 0.7. Replace I emitter by beta DC plus 1 I base, because beta DC I base is I collector. So we end up here with one equation where the only unknown is I base. It's 10 minus, I write it here as 7, it's actually 0.7. So I should put 0.7 here. So we solve for I base. Beta is equal to 100, then you get here 101. So you can see this one here is 101. And this multiplying this term here multiplying this 10K here, so this will give us over 1 mega ohm. You sum to this one, you get 1.1 mega ohm. So you get 9.3 over 1.1 mega ohm will give you 8.45 microampere. Very small current. Once we know the base current, we know the collector current is equal to 100 multiplied by I base. We know the emitter current is equal to 101 multiplied by I base. So we know the currents everywhere. So the collector current simply multiply by 100, you get 0.845 milliampere. If you want to find VCE, which is the voltage between the collector and the emitter, is equal to VCC minus I emitter multiplied by RC. I emitter is equal to I collector plus I base. They are actually, you can see they are very close, 0.845 and 0.5, very close. So sometimes we simply ignore the base current. You multiply this one by the 10K, which is this collector resistance here, you end up with 1.5 volts. And 1.5 volts greater than VCE sat, meaning the transistor is still in saturation, is still in the forward active region and is not in saturation region.